Hello friends, this is actually an online class for tutorial assistance on an NPTEL course, Computer Methods of Structural Analysis, which is hosted from IIT Madras. I am Professor Srinivas Chandrasekharan from Ocean Engineering Department at IIT Madras. This course is actually running for the past 6-7 weeks. You must have gone through the lectures in Module 1. This course essentially has many features. The specialty of this course is actually a computer program based teaching which enables you to write simple programs to solve complicated problems in structural analysis, then introducing you to offshore structures, types of offshore structures, then dynamic analysis, then advanced analysis like fatigue analysis, etc. I thank all the viewers who have joined this course, who are continuing to register for this course and enjoying the lectures. I hope you have been following the discussion forum very regularly, and I am sure you are able to submit the tutorials without any hassle. You will have no issues related to the submission of tutorials, I suppose. When I look into the discussion forums, I personally try to answer all the questions along with the support given by my teaching assistants. A few common questions which will be interesting to all of us can be the following. People wanted to know what would be the details of computer programs used for solving various problems. I am sure each lecture shows the detail of the computer coding. However, for your simplicity, today we have uploaded the computer program which is MATLAB based. For solving a variety of problems. For example, for solving an orthogonal beam problem, for solving non-orthogonal frame problem, for solving orthogonal frame problem, for solving truss problems, and also the computer code for solving 3D problems. Please look into the discussion forum for details. We have uploaded all the programs with MATLAB coding today in the morning. So simply look at the PDF files of each of the program. It contains the program coding. It contains sample input file. It also contains the sample output file, which is obtained from the computer code using MATLAB. I hope you will be enjoying the MATLAB support extended by MathWorks US. There's a free registration for this particular program. which can be used as a link along with this course with NPTEL. Each line by line of the program coding is explained for all the kinds of problems. I'll be happy to take any live questions if you really have, because we have about 6 tutorials we have floated. I am happy to see the maximum response given by the participants. I am not seeing any specific technical questions which causing confusion for solving these problems. One major doubt which you may have is about the type of questions during the major exam. Let me open out this. The questions are going to be simple. You do not actually have to use any computer program. Use any computer program to solve these problems in the exam. The exam is going to be offline. You simply need only calculators and the basic understanding of the problem. Friends, there is a common question which is again asked by many set of participants. What is the use of computer program based course when software exists for solving such problems? That's a very interesting question. Software is actually a black box. We all agree that the input which is taken for solving the problem is not explained but only shown graphically. If you accept that this statement is true in many of the software, I'm not criticizing using of software for computer analysis, but if you accept that the input file created by you is only shown back graphically, it has got series of issues. Let's say, is the input taken correctly? Is the input used correctly? Suppose if the output what you get is not desirable, how do you check the solution? Because to check the solution again, you need to create an input. So there's going to be a chain which doesn't enable you to solve actually your problem. So therefore, friends, it is important that if you learn how to write your own coding, then problem formulation is simple and well understood. Now, this is very important because in offshore structures, the structural system what we use are novel and they are non-traditional systems. I should say non-traditional in the sense, many of the common software cannot solve problems related to offshore structural analysis. For example, if you're looking for a new type of platform geometry, which we explain in other courses of NPTEL. However, let's say I am talking about a new type of geometry, which is triceratops. It has got a very complicated structural form, okay, which is non-standard. If it is non-standard, it cannot be actually used by any common software. So if I want to analyze this, I need to have the computer code. So we have to start understanding the computer programming and then use it for our own design. So that's the idea of the whole course. However, friends, you will all agree and you will appreciate that the new structural forms need a detailed understanding of analysis procedures. Though there are many textbooks available in this current context, but in IIT Madras at NPTEL, we prefer to teach this course line by line, step by step, so that a common man who is having a basic engineering idea with multidisciplinary nature can also intuit to follow the programming language easily, use MATLAB, and subsequently solve simple to very complicated problems in 2D and 3D analysis as being explained in the course content. So there are about 6 to 7 tutorials which we have floated now. We will be floating another 4 to 5 more. Those who have missed the early tutorials, no need to bother. You can still work out these tutorials and try to submit them. I have the following request to all the viewers. Do share your doubts, if any, your views, I should say, if any, in the ask a question forum. You can also send me email at drsekaran@iitm.ac.in. You can also give your feedback directly to NPTEL site. The whole idea is to make your learning more comfortable and more user-friendly. So actually it is a classroom coming down to your level to understand. If you really feel that the computer codes given in the course are not sufficient or non-executable, I urge to follow the basic tutorials given by MATLAB in the beginning of this course to really follow the coding procedures. The more interesting feature, which I am going to discuss now, we are able to solve the problem by hand computation, using a simple calculator. The same problem by computer program which has been given to you as an open source code. You will appreciate that both the answers tally to second decimal place. The content or the style, or I should say the pattern of analysis uses a repetitive procedure which is not problem specific. That's very, very important. It is not problem specific. It is highly generic. So that's the catch. We are using a very generic principle to solve the problem, or I should say set of problems. I'll be happy if you have any online direct live questions or any views to be shared. We can discuss that so that the benefit can be passed on to all viewers who are at the moment online. A common doubt which may come before you ask a question is, sir, I do not understand high level analysis, or I should say mathematics. Therefore, I lose interest in the course. The answer to this question is very simple. The procedure which is being used in the course needs higher order mathematics, I agree. For example, matrix methods. But there are standard subroutines available in MATLAB which you can use directly. For example, you want to take inverse of a matrix. The matrix size is very large, let's say 12 by 12, because it depends upon the unrestrained degrees. You do not know how to take an inverse of a 12 by 12 matrix. Use the MATLAB subroutine directly to prepare what we call SKUU inverse. Similarly, you may require MATLAB assistance for matrix multiplication. We can even do this with the MATLAB subroutine. For your sake, let me reiterate, we'll take a simple problem now. We'll try to solve this in a few minutes. I'll give the basic input on the screen. Then I will show how this input is transferred to the MATLAB coding line by line. You can run the problem. If you have any specific questions at this moment, I am happy to take the question before you do this exercise. So we'll do a simple problem for the benefit of the viewers because it's recorded. You can see it later. We'll explain this line by line so that you know how to use the MATLAB input directly from the source code. To start with, we'll take a simple beam problem. I'll do a few examples. We'll take a simple beam problem with one end fixed and other end on rollers. Let's take a two-span beam. We'll mark the data of the beam as shown in the figure. Let's say this is E and I. This is E and 1.5 I. Let's say we want to change the moment of inertia for the span BC. Let's say this beam has got a central concentrated load of 50 kilonewton on the span AB and a uniform distributed load on the span BC, which is 30 kilonewton per meter. Let's say AB is of span 5 meters and BC is of span 4 meters. We want to analyze this problem. So the question asked is, analyze the beam for the given loading. That's the question asked. Okay, that's the question asked. Maybe 10 marks. We can use any method to solve this problem, but we are interested to solve this problem using computer coding, using direct stiffness method, which I have been so far discussing. Let's see how do we do this problem, how do we start doing this problem. You know, step number 1, if you recollect, is identify the degrees of freedom of the problem. The moment I say degrees of freedom, there are two sets of degrees of freedom. One is what we call unrestrained degrees of freedom. Other is restrained degrees of freedom. We usually mark unrestrained in green color and restrained in red color. Let us try to mark the unrestrained and restrained degrees of freedom for this given problem. If you look at the support A, it is fixed, so it has no unrestrained degrees. Okay, all are restrained. If you look at support B, it is simply supported or hinged. So it has got one unrestrained degree, which is rotation, and one restrained degree, which is vertical displacement or vertical reaction in terms of forces. If you look at support C, the same story. It has got one unrestrained degree and one restrained degree. Let us mark this. So I am going to mark this as theta 1, this as theta 2. These are two unrestrained degrees. And then onwards, I am going to mark the restrained degrees. This is theta 3, okay, delta 4, delta 5, and delta 6. So there are total 6 degrees of freedom. 2 of them are unrestrained degrees and 4 of them are restrained degrees. Do you have any doubt in marking these degrees of freedom? Let me ask you this question. Is anybody online at this moment? Please share your views. Do you have any doubt in marking the degrees of freedom at this moment? It is very simple to identify an unrestrained degree and a restrained degree for a type of support. Please understand, this depends upon the kind of support. It is independent of the type of loading which is coming on the beam. Okay, I think we know this very clearly. So support A is fixed, therefore there is no unrestrained degree. Support B and support C are simply supported, therefore there are one unrestrained degree respectively in each support and one restrained degree on each support. Now very interestingly, in this particular solution pattern, we neglect axial deformation or axial displacements. The moment I say I am neglecting axial displacement, then what will be the size of my matrix? The size of my matrix, size of my stiffness matrix of the member will be 4 by 4. Okay, there are only 4 degrees of freedom for a fixed beam, 2 rotations, theta 1 and theta 2, and 2 displacements, delta 3 and delta 4, which we can always refer back to previous lectures in earlier module. Now I have the stiffness matrix to be generated. There are two members here. You can see that. Member AB and member BC. So member AB and member BC. Let's see what are the labels of these members. So let us mark the local axis of the member. This is XM axis. This is YM axis. We know YM is related anti-clockwise 90 degrees to XM, and XM is always in the direction of progression of the length of the member. So we have marked XM and YM axis. So two-dimensional analysis. Now I want to identify the labels for the member AB and member BC. The moment I say labels, the member AB will have the following labels. Okay. So theta 3, theta 1, delta 4, and delta 5. On the other hand, the labels could be 3, 1, 4, and 5. That's for the member AB. So please understand there's an order we are following to mark the labels. Rotations at J at the end, rotation the K at the end, then displacement at the J at the end, displacement at the K at the end. That's how we are marked. So friends, can you give me the labels for the member BC if you are online? Member BC obviously has again 4 labels. 1, that's rotation. Then 2, that's again rotation at C at the end. Then 5 and 6. So now my KAB, which is stiffness matrix of AB, will have labels, which is going to be a 4x4 matrix. KBC will again have labels, which is going to be a 4x4 matrix. The labels of AB, as you see here, will be 3, 1, 4, 5, 3, 1, 4, 5, 3, 1, 4, and 5. Similarly, if you look at BC, 1, 2, 5, 6 are the labels. Let's enter 1, 2, 5, 6, 1, 2, 5, 6. So friends, identifying the labels is one of the important input for the computer program. Once I identify the label, let's say I have this matrix coefficients. Let's say I have these coefficients written. We all know it's very simple to identify and remember these coefficients. For example, this value, the star value here, is nothing but 4 EI by L. Let's see what is this value for the member AB. 4. Let us retain E as a known value and I as a simple number. We are not substituting for this. And L for this member will be 5 meters. So I'm using units as metric, SI units. So it's going to be 5. So it's going to be essentially 0.8 EI. If you say EI is constant out, I should enter this value as 0.8. Once I have this value, I can fill up this matrix as 0.4. And this will be 1.2 by 5 minus 1.2 by 5. Once I have the first column filled up, the second column is simply cross of these, and this will remain as same. Once I filled up the second column, the third column will be 1.2 by 5, 1.2 by 5, and this will be sum of these two. That is 2.4 again by 5. And so on. So one can fill up this. So you know, this matrix is available for easy to remember, because if I say this is going to be 4EI by L and so on. Similarly, I can fill up this matrix also if I know the length of the member BC, which is in this case 4 meters. Is there any doubt for anybody in identifying and preparing these two matrices KAB and KBC? So now once I have these two matrices KAB and KBC with me, KAB and KBC with me. Then I got to assemble these matrices to form a total stiffness matrix of the whole structure. That's very interesting. A common doubt which people had initially in the discussion forum is, what would be the size of this matrix? Let us go back to the question again. The beam has got total 6 degrees of freedom. You can see here 1, 2, 3, 4, 5, 6. So essentially, the stiffness matrix of the whole beam will be 6 by 6. But interestingly, each member has 4 by 4. So what I am going to do here is, I am going to overlap these two and condense them into a 6 by 6 matrix. So the labels for this will be starting from 1, 2, 3, 4, 5, and 6. And 6. So what I am going to do is, what is the value of 3, 3? I am going to enter this value here. Okay, 3, 3. Then if you want to enter 1, 1, I'll go back to this, pick up 1, 1, and also pick up 1, 1, add these two, and enter it here. Okay? It's very easy to assemble this matrix and get the K bar or the global matrix for the member ABC. That's for the whole beam. Of course, you remember EI will be constant because E and I in both the members are same. But however, please note, this beam has 1.5 I, this beam has only I. So when you do this, I will use this 1.5 as a multiplier here. For example, this will be 4EI by L, which will be 4E into 1.5 I by 4, because the length of the member BC is 4 meters. So EI is constant, this value is going to be 1.5. So this matrix can be easily filled up without any confusion, and therefore this matrix can be formed automatically using the computer program. Okay, so this is an input which is generated. Now this problem has how many understand degrees of freedom? Is anybody online? Please give me an answer. How many understand degrees this problem has? They have been marked in green color. Okay, there are 2 understand degrees, theta 1 and theta 2. Therefore, I partition this matrix. I partition this matrix at 2 by 2. Okay, at 2 by 2. So this becomes my KUU. This becomes my KUR. This becomes my KRU. And this becomes my KRR. How do I get this? This is understand degree. This is restraint degree. This is understand degree. Restraint degree. If you want to read this, row first, column next. So KUU. If you want to read this matrix, row first, column next. So KUR. Similarly, KRU and KRR. So the program will plug out this value, KUU, and then it will find the inverse of this matrix using MATLAB. Okay, friends? So inverse is uptime. That's step number 2. In step number 3, we want to find the joint load vector. So many people had confusion in this joint load vector. So it's very simple. I must first find the fixed end moments and reverse the sign to get joint load vector. Let us see how we are going to do this. We'll spend another 5 minutes to solve this problem and complete. Let's pick up this. So this is my loading. AB is 50 at the mid span. Let me write down that here. Let's say I am drawing the problem again. A, B, and C. So that's a mid-span loading of 50 kilonewton. Okay. And there's an UDL of 30 kilonewton per meter, I suppose. Let's verify this. is 30. Yeah. And 5 meter and 4 meter. Okay. So let us mark these values here. 5 meters and 4 meters. Let's now draw AB separately and BC separately. Okay. So central concentrated load. So the moments are going to be PL by 8. Okay. Please note down the sign convention. Here is UDL. Therefore, this is going to be WL square by 12. So let us fill up these values. So this is going to be 50 into 5. That's the span of the beam by 8. So I can get this value. I can get this value. Similarly, this is going to be 30 into L square. That is 4 square by 12. Can get this value. This value. Okay. So let us find out these values quickly. So 250 by 8. So it's 31.25. 31.25 kilonewton meter. And this is also 31.25, but this is a minus sign. Similarly, this is going to be 30 into 16 by 12, which is going to be 40 kilonewton meter. And this is minus 40 kilonewton meter because this is clockwise. Now let us try to find ABC as a summary. Let's also find the reactions. This is going to be 25 and 25 kilonewtons because 50 by 2. And this is also going to be 30 into 4, 120. So 60 kilonewton and 60 kilonewtons. So now I want to summarize this very quickly for the joint load. So now this is going to be 31.25. And here there's a clockwise of 31.25. There's an anti-clockwise of 40. And here there's a clockwise of 40. And this reaction is 25. This reaction is 25. This is again 60. And this is 60. So this will be equal to an anti-clockwise of 31.25, a reaction of 25, and the reaction of 85, and a net moment, you see, net moment of 40 is clockwise, so anti-clockwise 40. So 40 minus 31.25 is going to be 8.75. And this is going to be 40, and this reaction is going to be 60. I want to now create the joint load vector for this. Okay, let us look into the degrees of freedom. Let us mark back the degrees of freedom. If you look at the degrees of freedom, 1, 2, 3, 4, 5, 6. Let's mark them here. Okay. 1, 2, 3, 4, 5, and 6. Okay. So I'm going to mark down these values 1, 2, 3, 4, 5, and 6. So I'm going to create a joint load vector. Joint load vector is a reverse of sign of fixed end moments. Let's look into this figure now. So now if you look at 1 is anti-clockwise. So it's anti-clockwise here minus 8.75. Why there is negative? Because this anti-clockwise should be reversed as clockwise, whereas the original sign is anti-clockwise, so minus. Similarly, 2 is anti-clockwise. This is to be reversed anti-clockwise. This and this matches, therefore plus 40, 40.0. Similarly, for 3, minus 31.25. Similarly, for 4, minus 25.0. 5, minus 85.0. 6, minus 60.0. Friends, this is an input which I got supplied to the program. Once you have this input ready, then the next step is very simple, and that is the final step we have. So we know I want to find delta U, which will be KUU inverse of JLU. The U stands for unrestrained degree. So we can get this from the solution using a program. Once I get this, I can find the end moments as simply for the ith member is k of the ith member into delta of the ith member plus fixed end moments of the ith member. All I have now, okay, I can substitute this and get the reactions of each member, which we are going to now do it using the computer program. So please follow the computer program now, step by step, and see the input what we have given is going to be fed. Let's quickly see what are the inputs required for this problem. Input is degrees of freedom. Then the details about span, moment of inertia, Young's modulus, etc. Then the labels for the problem, that is for each span, what are the labels? Once I have the labels, then I have to also give the joint load vector. Then the program will find out K. The program will find out KUU inverse. The program will find out delta U. Then the program will find out moments of the forces. Let us share the screen now and see how the program is explained line by line. I have Miss Vinodini with me, who is also the teaching assistant, who is sharing her thoughts and her ideas during the discussion forum. So I'll request Vinodini to share the screen and explain the computer program line by line with respect to this problem. Let's quickly see the problem once for a minute again. The problem is actually a two-span beam. The number of members are going to be 2. The degrees of freedom are marked here. So I'll put the screen on the side and parallelly the computer program screen on the other side. You can compare the answers and try to find how the input is actually matching with the screen sharing mode, and line by line the program will be explained. If anybody online at this moment, if you have any doubt, you can please stop me and ask me if you have any difficulty.
This is the program for stiffness matrix method for solving a 2-beam problem. So here we have the inputs. These are the inputs required for running the program. First comes the number of members. So the problem solved now has 2 members. So we have given 2 here. And the next input required is the moment of inertia. For the first member it is 1, and for the second member it is 1.5. Then the length of the members, each members is 5 meters and 4 meters. Then the number of unrestrained degrees of freedom, it is 2. And the number of restrained degrees of freedom is 4. And the global labels corresponding to the unrestrained and restrained degrees of freedom are 1 and 2 for unrestrained, 3, 4, 5, 6 for the restrained degrees respectively. Then the global labels for member 1, 3, 1, 4 and 5. Global labels for member 2, 1, 2, 5 and 6, and this line of the program is used for combining both the global labels into a single matrix. Then we are calculating the degrees of freedom for the particular structure of the problem. It is the sum of the number of unrestrained degrees and the number of restrained degrees. Then we are defining the total stiffness matrix, the size of the total stiffness matrix, which is going to be degrees of freedom. Here the degrees of freedom is 6, so the total stiffness matrix is going to be of size 6 by 6. Then the input required is the fixed end moments for both the members. For member 1, it is 31.25 minus 31.25. These are the moments. 25 and 25, plus 25 and plus 25 are the reactions. For the member 2, the moments are plus 40 and minus 40, and the vertical reactions are minus 60 and minus 60. And the final input that we need is the joint load vector. Here the size of the joint load vector is 6 by 1, corresponding to the degrees of freedom of the structure. So that is given here. Minus 8.75 plus 40 minus 31.25 minus 25 minus 85 and minus 60 as explained by professor. And then the number of unrestrained degrees of freedom. Joint load vector corresponding to unrestrained degrees is 2. So the first two values are written here again. Then we have the program for the stiffness method. So the first step is the calculation of rotation coefficients for finding the stiffness matrix. So here we have RC1 and RC2. These are the rotation coefficients. For EI by L, here E is taken as constant, so we are not mentioning it over here. And RC2 is 2I by L. Again, the derivation of the stiffness matrix. Here we are neglecting the axial deformation, and so the size of the stiffness matrix is going to be 4 by 4. So these K1, K2, K3 and K4 are the stiffness coefficients. We are deriving it column wise, and this line of the program is for combining all these 4 columns into a single matrix. And then this line is for printing the stiffness matrix, and again we are getting the local stiffness matrix for the first member. So we are giving all these values in a for loop. So this loop will run from 1 to n. N is the number of members. So for the first member, first you'll be getting the local stiffness matrix. And this portion of the code is for mapping. Here we are mapping the local stiffness matrix into the global stiffness matrix corresponding to the global labels. Now we are getting the K total for the first member. The loop will run for n number of members. Here we have 2 members, so the loop will run twice. Finally, we'll get the total stiffness matrix of size 6 by 6. Now we are going to partition the matrix in order to find the unrestrained stiffness matrix. Here the number of unrestrained degrees of freedom is 2. So the size of unrestrained stiffness matrix is going to be 2 by 2. So this portion of the code will partition the total stiffness matrix to find the unrestrained stiffness matrix. Now this line will print the final output of the unrestrained stiffness matrix on the command window. Then let me increase the size of the font. So here, INV is a command used for finding the inverse of a matrix of size n by n. In this line, we are calculating the inverse of unrestrained stiffness matrix, which is required for the calculation of displacements. So the next step is the displacement calculation. Del u is equal to KUU inverse multiplied by the joint load vector of unrestrained degrees. So the displacements will be calculated now, and the same has been displayed in the command window, and for that purpose we have included these 2 lines. Next we are including the displacement in the restrained degrees, which is going to be 0, and the size of the displacement in the restrained degrees is 4 by 1, since the number of unrestrained degrees is 4. And in this line we are combining both the displacements in unrestrained degrees and restrained degrees into a single matrix. Now finally we are calculating the moments and the displacements, global displacements and global end moments. So that portion will be done under this part of the code. So we have 2 members. For displaying the output of both the members, we have included all these lines. This is for the first member, and this portion is for the second member. So del bar is the global displacement matrix for members 1 and 2, and m bar will be the global end moment matrix for members 1 and 2. So this is the editor window of MATLAB, and now I'm going to run the program so that we can see the output. So the program is executed now. Here we have the outputs. So for the local stiffness matrix of member 1 is given here, and for the member 2, this is the local stiffness matrix of size 4 by 4, since axial deformation is neglected. And the total stiffness matrix is here for the whole structure, and it is of size 6 by 6. We have 6 columns and 6 rows. And the unrestrained stiffness matrix is here of size 2 by 2. Here we have the inverse of unrestrained stiffness matrix, the joint load vector that has been given as the input. Now the unrestrained displacements of size 2 by 1. And this is the final output we have for member 1 and member 2. And these are the global end moment matrix, end moments for member 1. And this is the end moments for the member 2. So you can see the moments at member 1 and member 2 are matching at joint V.
So friends, the data what we have, we have used this data and we have solved the problem using the computer code, and the code was explained line by line by the teaching assistant. I am sure you would have intuited to write a simple coding to solve a problem like this, and I urge that you should share your views and doubts if you have any in the Ask a Question forum. I am happy to get back to you again in the online session if you request again to the discussion forum. So we have solved one problem step by step and explained you the procedure. So I'm happy that we'll be able to get back to you again if you have any specific questions or doubts. So friends, I hope the mission of NPTEL at IIT Madras is to make the teaching interesting, simple, and state-of-art learning. We are doing our best to give you the tools of teaching and analysis in a most simple form. I take this opportunity to also thank MathWorks United States to give a free login to use MATLAB for this particular course. I also thank NPTEL administration and my team of research scholars and my faculty colleagues who have put in effort to train and educate me in this domain of research. Thank you very much and bye.